This video is to support a course that I'm teaching in elementary number theory, and this is the 12th such video. And here we're going to look at Euler's generalization of Fermat's little theorem, but we'll prove it from scratch, and Fermat's little theorem will be a corollary. Okay, so to get started, let's define Euler's totient function, which is generally denoted by phi. It goes from the natural numbers to the natural numbers. And what does it do? Well, it counts the number of natural numbers between 1 and n that are relatively prime to n. So that's the output of phi. Then we want to define something called the reduced residue system modulo n. So a reduced residue system modulo n is a set of integers b1, b2, b3 up to b phi n, such that the GCD of BR with n is 1. So in other words, every one of these numbers is relatively prime to n. And then furthermore, if R is not equal to S, then BR is not congruent to BS modulo n. So these are all incongruent mod n. And furthermore, they are relatively prime to n. Okay, great. So I've got some examples cooked up so that we can get an idea of phi of n and some reduced residue systems. So let's start with n equals 4. So the first thing that you would probably want to do is write all of the numbers between 1 and 4 that are relatively prime to 4. So that'll just give you the number 1 and the number 3. So that tells us that phi of 4 is 2 because there are 2 guys in this set. And then from that point, you can come up with some other reduced residue systems. So some other good choices would be -1 and 1 and 3 and 5. Okay, so let's look at the case when n is equal to 8. So again, to start, you would want to find all of the numbers between 1 and 8 that are relatively prime to 8. So in this case, you get 1, 3, 5, 7. So that means phi of 8 is 4. But some other reduced residue systems would be as follows. So -3, -1, 1, 3, and 5, 7, 9, 11, although there are clearly infinitely many choices. Next, phi of 10 is equal to 4. That's because there are 1, 2, 3, 4 numbers between 1 and 10 that are relatively prime to 10. Another kind of choice for a reduced residue system would be 7, 9, 11, and 23. Okay, so one more example. Phi of 9 is equal to 6. That's because there are 6 numbers between 1 and 9 that are relatively prime to 9. We've got 1, 2, 4, 5, 7, and 8. Notice we had to skip 3 and 6 because those are not relatively prime to 9. Okay, so now that we've got these examples to get us thinking concretely about these two definitions, let's prove a lemma which will help us prove Euler's theorem. Okay, so let's look at this first lemma. So we want to start with a reduced residue system modulo n, which is given by the set of integers b1, b2, b3 up to b phi n. And next, we pick any integer a that is relatively prime to n. So in other words, the GCD of a with n is 1. Then from these two parts, this integer and this reduced residue system, we can construct a new reduced residue system. And that is given by all a multiples of our original reduced residue system. So to be more specific, the set a times b1, a times b2, all the way up to a times b phi n is also a reduced residue system. Okay, so let's see how this proof goes. So the first thing that we want to show is that the GCD of any element from this new set with n is 1. So let's do that. So we'll do that with a little claim within the proof. So for all I that is between 1 and phi of n, we want to show that the GCD of a bi with n is equal to 1. Great. So that's one condition of being part of a reduced residue system. Okay, so we're going to do this by contradiction. So let's suppose not. So that tells us that, well, first of all, the GCD of these two numbers is bigger than 1. But if it's bigger than 1, then that GCD has some prime divisor. So let's say there exists a prime, we'll call it P, such that P divides A times BI and P divides N. So P is a divisor of the GCD, which we're supposing is not equal to 1. But let's notice that this condition right here says that P divides A or P divides BI. And now let's look at those cases individually. So if P divides A, then that means that P divides A and P divides N. Remember, that's part of our setup. P is divisible, or N is divisible by P. But putting these two things together tells us that P divides the GCD of A with N. But remember that the GCD of A with N was 1. So we've got a prime that divides 1. But that's clearly a contradiction because 1 is not divisible by any prime. So now we move down this other branch, which is P divides BI. Well, notice P already divides N, so that means we have P divides BI and P divides N. But if it divides both of those, it divides their GCD. So we've got P divides the GCD of BI with N. But now let's recall that these B's form a reduced residue system, so we know this GCD is 1. So we've got P divides 1 again, which is again a contradiction. So what did we contradict? We contradicted this supposition that the GCD is not equal to 1, which means this GCD has to be equal to 1. Okay, so what do we have so far? We've got all of these numbers in this set are relatively prime to N. And that's the first condition that we need for this new set to be a reduced residue system. Okay, let's get rid of this and we'll prove the other condition. So far we've chosen that all of the numbers here are relatively prime to N, but we still need to show that they are all incongruent modulo N. So in other words, for all I not equal to j, where I and j come from the range between 1 and phi of n, we have a times bi is incongruent to a times bj. So how can we do that? Well, we'll start by setting up a congruence and show that that means that I is equal to j. Okay, so let's do that. So let's suppose ABI is congruent to ABJ modulo n. Okay, but then by the definition of congruence modulo n, that means that n divides A times the quantity BI minus BJ. Okay, now we can take that divisibility relationship and write it as a multiplication problem. So this means ABI minus ABJ is equal to n times k for some integer k. So that's by the definition of divisibility. Next, what we want to do is somehow use the fact that the GCD of A with n is equal to 1. And the classic way to do that is to impose some sort of Bézou's identity. So let's pick, I'll call them x and y, which are integers, such that ax plus ny is equal to 1. So again, why is that possible? That's because the GCD of A with n is equal to 1. Now, how can we smash these two equations together? Well, we can do that maybe by multiplying this equation by x and then solving this for a times x. Notice if we multiply this equation by x, we'll have a times x here, a times x here. And then if we solve this for a times x, well then maybe we're off to a good start. So first of all, we'll solve this, leaving us with ax is equal to 1 minus n times y. And then simultaneously, we'll multiply this equation by x, leaving us with ax bi minus ax bj is equal to nxk. But now we can do some substitution. So we'll substitute this into ax in both of these equations. So we have 1 minus ny times bi minus 1 minus ny times bj is equal to nxk. Okay, but we're about to reach some sort of problem. So let's notice that this guy will distribute through and give us a multiple of n. This guy will distribute through and give us a multiple of n. And then this guy is already a multiple of n. So that means we can rearrange all of the multiples of n over on the right-hand side of the equation and take everything which is not a multiple of n on the left-hand side. And that'll be this 1 times bi and this minus 1 times bj. Okay, so let's just do that real quick. So we'll have bi minus bj, that comes from these blue parts, is equal to n times a bunch of stuff. And I'm not going to worry about what that stuff is. Notice it's made up of xk. It's also made up of y times bj and y times bi. But the important part is it is a multiple of n. But if bi minus bj is a multiple of n, then that is the same thing as saying that bi is congruent to bj mod n. But then, because these b's make a reduced residue system, that implies that I is equal to j by this condition down here on reduced residue systems. Okay, so that's the end of the proof of this lemma, and now we're ready to prove Euler's theorem. Now, armed with our previous lemma, we're ready to prove Euler's theorem, and that says if the GCD of a with n is 1, then a to the phi of n is congruent to 1 mod n, where again, phi of n is this Euler's totient function. Okay, so since that lemma used the notion of a reduced residue system, the proof of this theorem should probably invoke reduced residue systems. So let's let B1, B2, all the way up to B phi n be a reduced residue system modulo n. And then our lemma implies that we have another reduced residue system modulo n, and that is given by a b1, a b2, all the way up to a b phi n is also a reduced residue system. But let's recall what a reduced residue system is. It's a list of all possible residues modulo n that are relatively prime to n. So what does that tell us? That tells us that a b1 times a b2 all the way up to a b phi n is congruent to b1, b2 all the way up to b phi n, and that's occurring modulo n. And why is that? Well, that's because we're multiplying all possible residues modulo n just two different ways. One with our original reduced residue system, and one with our new reduced residue system built out of our original one and the number a. But let's notice that this is equal to a to the phi of n times x, where maybe we could say x is this product b1 up to b phi n. And then the right-hand side is just x mod n. And then finally, we can make the kind of obvious observation that the GCD of x with n is equal to 1. Well, that's because it's the product of a bunch of things that are relatively prime to n. But what does that mean? That means it has an inverse modulo n. We can multiply both sides by the inverse modulo n, and that leaves us with a to the phi of n is congruent to 1 mod n. which is exactly where we wanted this theorem to end. So now that we've got this taken care of, let's look at a quick corollary, which is famous in its own right as Fermat's little theorem. Okay, so as promised, we're going to look at a corollary, which is the famous Fermat's little theorem. So for this, we want to assume that we have a prime number called p and an integer a that is not a multiple of p. So in other words, p does not divide a. Then the conclusion is that a to the p minus 1 is congruent to 1 mod p. So why is this such a quick corollary? Well, that's because when you're dealing with primes, saying p does not divide a is equivalent to saying that the GCD of a with p is equal to 1. And then furthermore, phi of p is equal to p minus 1. Well, let's just think about that. You're counting up all of the numbers between 1 and p that are relatively prime to p. Well, that's clearly going to be everything except for p, so that's why we get p minus 1 there. Okay, so let's finish this video off with some examples. As an example, we're going to look at a very classic number puzzle, and that is to determine the last 2 digits of 7 to the 950. So obviously 7 to the 950 is enormous, so it would be pretty much impossible to calculate that number easily. So finding the last 2 digits is maybe as good as we can do. And how would you do that? Well, notice that the last 2 digits are equivalent to reducing this thing mod 100. That'll leave us with only the last 2 digits. Well, I want to point out that at this stage in the course, we don't know how to compute phi of 100 or phi of n easily. So instead of computing phi of 100, what we'll do is compute 7 to the 950 mod 4, and then also 7 to the 950 mod 25, and then put our final answer together using the Chinese remainder theorem. So in the future, we will have a quick way to calculate phi of n if we're given some small-ish value of n, but at this stage in the course, we don't. Okay, well, let's first notice that phi of 4 is equal to 2. So that's pretty obvious, right? And then also that 950 is equal to 2 times something. And that something is 475. Well, it's obviously a multiple of 2 because it ends in a 0. So that means we can take 7 to the 950 and rewrite it as 7 squared to the power of 475. And then use the fact that phi of 4 equals 2, applying Euler's theorem, to say that this is congruent to 1 to the 475, which is congruent to 1 mod 4. So far, we have 7 to the 950 as congruent to 1 mod 4. Now we'll figure out what it is congruent to mod 25. Okay, so first we need to calculate phi of 25. Like I said, we don't have a quick way of doing that yet. So we'll just say it's the number of the elements in the following set, 1 up to 25, minus all of the multiples of 5. And we know that we only have to subtract off the multiples of 5 because 25 is equal to 5 squared. So that's a nice trick here. And so that means we need 5, 10, 15 are gone, 20 and 25 are also gone. So let's notice there are 25 elements in this set. There are 5 elements in that set. So in the end, we have 25 minus 5, which equals 20. Okay. So now we want to take this 950 and do division with remainder with 20 so that we can use Euler's theorem with 25. So let's notice that 950 is equal to 20 times 47 plus 10. So that's our remainder after dividing by 20. Okay, so that means that 7 to the 950 will be equal to 7 to the 20 to the 47 times 7 to the 10. Just using exponent rules. But we know 7 to the 20 is congruent to 1 mod 25. So 7 to the 10 is what's left over. We have 7 to the 950 is congruent to 7 to the 10 mod 25. Okay, so we're running out of room there, so let's get rid of some of this calculation and then we'll finish it off. So on the last board, we determined quickly that 7 to the 950 is congruent to 1 mod 4, and that 7 to the 950 is congruent to 7 to the 10 mod 25. Now we want to make this last calculation. And at this stage, there's no real quick way to do this, so we'll just take some powers of 7 until maybe we see some sort of pattern. So notice that 7 to the 1 is 7 mod 25, so we don't really need to worry about that. 7 squared is equal to 49, which is equal to 50 minus 1. So that means it's congruent to negative 1 mod 25. But that's actually extremely helpful because now we can see that 7 to the 10 is the same thing as 7 to the 2 to the 5th power, but 7 squared is negative 1, so this is negative 1 to the 5th power mod 25. But then negative 1 to the 5th power, well, since 5 is odd, that's going to be congruent to negative 1 mod 25. But now we probably want to go back to positive numbers, so negative 1 mod 25 is the same thing as 24 mod 25. So this trick of working with negative numbers when they're small is really powerful whenever you're doing this kind of simplification. Okay, so let's bring that up. Okay, so far we've shown that 7 to the 950 is congruent to 1 mod 4 and 24 mod 25. And from here, it may not seem where we need to go, but luckily we've got something called the Chinese remainder theorem. So if we take the system of congruences given by x is congruent to 1 mod 4 and x is congruent to 24 mod 25, then we can solve that with the Chinese remainder theorem, which the last video was about. So we're not going to do all of the details of the Chinese remainder theorem. But since the GCD of 4 with 25 is 1, we're guaranteed to have a solution. So I'll just say, yes, we will have a solution. And we're guaranteed to have uniqueness mod 4 times 25, in other words, mod 100. So that means we'll have exactly the solution that we need. So like I said, we won't work out all of the details. It's in the previous video, and really it's just kind of a calculation. What you'll see is that x is congruent to 49 mod 4 times 25, or mod 100. So putting all of that together, we see that our number, 7 to the 950, is congruent to 49 modulo 100. In other words, the last 2 digits of 7 to the 950 are 49. So let's maybe get rid of this and we'll give some warm-up problems that are built off of Euler's theorem and Fermat's little theorem. Okay, so here I've got some quick warm-up problems built around Euler's theorem and all of the parts that went into proving Euler's theorem. So first, let's find 2 different reduced residue systems modulo 15. Next, let's reduce 3 to the 999,999,999 mod 7. So what do I mean by reduce that modulo 7? I mean you should output a number between 0 and 6. Okay, and then our last problem is to find the last digit of 3 to the 1,000. Okay, that's a good place to stop.